Everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 2, Differentiation, talking about the definition of derivative and the basic derivative rules. This video is our Chapter 2 review. I hope Chapter 2 went really well for you. Good luck on your review. Feel free to skip around as you're going through those review topics. Have a good day. All right, everybody, we're getting into the Unit 2 review on this chapter on differentiation. So talking about the definition and the fundamental properties of those derivatives and derivative rules. We're trying to get ready for our Chapter 2 test, and so we've got this review sheet, which we're going to go over in detail. As usual, the solutions are also posted with this video. Check those out, and you're welcome to skip around in this video if you want as well, if there's a particular topic that you want to see for review. All right, let's start with number one. So, actually even before that, remember that reviews do not cover all material from the lessons, but will hopefully remind you of some key points. To be prepared, you should review the packets and videos from Unit 2. All right, our first set of instructions says to find the average rate of change of each function on the given interval and use appropriate units if necessary. So a reminder that our average rate of change is equivalent to sort of like the slope between 2 points. And in general, we refer to the average rate of change as f of b minus f of a, all divided by b minus a. And that's for 2 points. One is a comma f of a, and the other is b comma f of b. Now, knowing that, in this first problem for number one, we're saying that the wx is the natural log of x, and we're saying it's between 1 and 7. So we're going to use these endpoints of this interval as our x values, or our a and our b. And so in order to do that, we're going to think about what coordinates we have. We have an input of 1. If we input 1 into w of x, that means the output is going to be the natural log of 1. And if we input 7, then our output is going to be the natural log of 7. So we're going to use these coordinates for that average rate of change. So that means that this is going to be the natural log of 7 minus the natural log of 1, all divided by 7 minus 1. If you remember your natural log graph, you might remember that the natural log of 1 is 0. If you look at the natural log of log graph, 1 comma 0 is on it. So this is going to then equal just the natural log of 7 divided by 6. And we can get some sort of decimal equivalent, but this would be our exact answer for number 1. Number 2, we've got a position function, it looks like. S of t is equal to negative t squared minus t plus 4, and we're going from 1 to 5. Here we're using interval notation for number 1. Now it looks like they're using, inequality notation for number 1. Now we're using interval notation for number 2. T represents seconds, S represents feet. So in this case, if we want to find the average rate of change, we're thinking about plugging in 1 for our input for this, and so we would have S of 1 as our output. We would plug in 5, we would have S of 5 as our output. And so if we're going to do this, this should be whatever S of 5 minus S of 1 divided by 5 minus 1. Well, what are those values equal to? If we plug 5 in to that S of t function, we have negative 5 squared minus 5 plus 4, and then we're subtracting S of 1, so that's negative 1 squared minus 1 plus 4, and that's all being divided by 5 minus 1, which is 4. If we wanted to evaluate that, this looks like we're going to have what? Negative 25 minus 5 is going to be negative 30, plus 4 is going to be negative 26, and then we've got negative 1 minus 1 is negative 2, plus 4 is going to be positive 2 over 4. And so this is going to be what? Negative 24 over 4, which would be negative 6 for our answer for that. Oh, I have to be careful. Let me step back. This was a minus here, so we're actually subtracting that. Let me fix that one real quick. So this is a negative 26 minus 2, and that's going to make this negative 28. Which if we divide by 4 is going to actually be negative 7 for this. So let me fix that real quick. So negative 28 over 4 is going to be negative 7. Now again, this problem asked us to use appropriate units if necessary. In this case, in the numerator, we were talking about the output of this, which is in feet, and our inputs here are seconds. So we have found a rate, right? It's an average rate of change. So in this case, this is going to be feet per second. -7 feet per second. For those of you in physics or have taken physics before, if this is our position function, we find the rate of change of the function. We have found, in this case, an average velocity over that interval. So between t equals 1 and t equals 5 seconds, whatever object that we're talking about traveled at a rate of -7 feet per second. So it was moving in the negative direction with a speed of 7 feet per second. Nice. Number 3, we are finding the derivative of y equals 2x squared plus 3x minus 1 by using the definition of the derivative. So we learned earlier in this chapter that there are sort of two different formal definitions of derivative using limits. They're instructing us here to use this particular one, which is our first one, and that's going to allow us to find the derivative function for this, which is nice. So let's plug in what we know. We're going to say the derivative of this, I'll call that y prime, we could also call that dy dx if we wanted to, is going to be the limit as h approaches 0 of f of x plus h. So x plus h is our input for this function. That means that for each of these x values here, I need to plug in an x plus h there, and we're going to end up having to expand. So this is 2 times x plus h quantity squared, plus 3 times x plus h minus 1. That part is our f of x plus h right there. And then now we need to subtract f of x. So minus the original function f of x, which was 2x squared plus 3x minus 1. That part that we've got is our f of x right here. And of course we're subtracting because it told us to subtract. And then we're just dividing that all by h. Next, what we're going to need to do is we're going to need to look at this part over here. A couple things we're going to have to evaluate here in the numerator. We're going to want to expand first. We're going to want to do x plus h times x plus h. We're going to want to distribute the 2 to each of those things. We're going to want to distribute the 3 to each of those things. And then this negative sign here, we're going to want to distribute to each of those terms inside of those parentheses. So if we do that, we're going to have that y prime is equal to the limit as h approaches 0 of 2 times x squared plus 2xh plus h squared plus, if we distribute 3x plus 3h minus 1 minus 2x squared minus 3x and then a plus 1, because again we distributed this negative sign to each of these terms that we've got right here. And of course this is all being divided by h. Now these types of problems can feel really intimidating because this numerator grew a lot. But the goal here is if we expand and then we cancel out terms that are opposites of each other, this should become much simpler once we do that. So let's see what we've got. We're going to want to next distribute this 2 to each of these terms. And we can also notice that some of the things are going to already cancel. We can see that this 3x is going to cancel with this negative 3x. We can see that this negative 1 is going to cancel with this positive 1. So what do we have in this next line? We've got y prime is equal to the limit as h approaches 0 of 2x squared plus 4xh plus 2h squared. We've still got a plus 3h and a minus 2x squared up in that numerator. But we can also see now that we've expanded all the way that our 2x squared and our negative 2x squared are going to cancel each other out, which means that this is going to become the limit as h approaches 0 of 4xh plus 2h squared plus 3h all divided by h. Now we can factor an h out of this numerator. If we do that, I'll just sort of do this as side work since we're running out of room. If we're to do that, that's going to be h times 4x plus 2h plus 3. And so if we do that, the h's in the numerator and the denominator are going to cancel each other out, which means that this is going to be equal to the limit as h approaches 0 of just that 4x plus 2h plus 3. Now there's nothing left to cancel, so we're going to go now and do our direct substitution, which means we're going to put h0 in for h in this equation, which means that the 2h is going to go away because that's 2 times 0, and we're just left with 4x plus 3. 4x plus 3 would be our derivative function for problem number 3. And for those of you who have gone ahead, hopefully at this point, if we're doing review, if you remember our power rule and we think about the power rule for 2x squared plus 3x minus 1, if we applied the power rule for that, that would give us 4x plus 3. So we have a good way of checking and making sure that our answer here makes sense and agrees with the power rule for problem number 3. Problem 4, for the function h of t, h is the temperature of the oven in Fahrenheit, and t is the time measured in minutes. Explain the meaning of the equation h of 15 is equal to 420. And in B, they're asking h prime of 43 is equal to negative 11. So first off, we want to pay attention to whether they're talking about the original function or its derivative. Right, the original function is going to use essentially what's given here and pretty much exactly in the way that it's described. When we see the h prime, we're going to have to recognize that that is a rate of change. And so let's see how these are different. First, if we're going to explain the meaning of h of 15 is equal to 420, again, the 15 is the time. So at 15 minutes, the temperature of the oven is 420 degrees Fahrenheit. So at 15 minutes, the temperature of the oven is 420 degrees Fahrenheit. So I know that this is the case because they're saying that it's h of 15, so 15 is our input, and it's equaling 420, so our h is the 420 here in this case. Explain the meaning of the equation now of h prime of 43 is equal to negative 11. So in this case, we're talking, because we see that little prime right there, it's talking about a rate of change. And so this negative 11 is not negative 11 degrees Fahrenheit, right? This isn't a very cold oven. This is actually saying that the rate of the oven is decreasing by 11 degrees per minute. So I would mention just sort of our units on this, even though it's not saying it explicitly. If you know that it's the rate, we're talking about degrees per minute here, given what they've told us in this problem. And so that's different because the last problem was just the degrees itself. And so here, how do we describe this? We're going to say, okay, at 43 minutes, so at 43 minutes, so the time is still the same, that's our input, the temperature of the oven we would say in this case is decreasing. It is decreasing. It's getting smaller by 11 degrees per minute. So at that particular moment, we are saying that the temperature of that oven is decreasing by 11 degrees per minute on that at 43 minutes. Nice. So, this is a big part of the AP exam as well. Thinking about for number 4, right? We want to not only be able to find derivatives, but we want to interpret what a derivative statement means. This is a super common thing where they're giving you some sort of context, and then they're asking you then to figure out what this statement means in terms of the original context. Notice that, I took into account the time, I took into account the rate, I gave units in my answer. I said that it was decreasing here because we saw that it was a negative. If it was positive, we would say that that rate was increasing. And then, brought it back to the fact that we're talking about the temperature of an oven. So really tying all of those things into your statements is a great way to make sure that you get all of your points in these types of problems. All right, on to number 5, find the derivative of each function. So we've got a bunch of derivative rules that we've learned in this chapter. Let's use them. Number 5, we want to try to apply the power rule for this particular problem, except I can't apply the power rule while this is in the denominator. So what I'm going to do is I'm going to use some negative exponents to rewrite this function. F of x is going to be equal to 4 minus, this is going to be, well, it's still 1/2, so 1/2 times x to the negative 2 power. So it's okay that that's a 1/2 for that coefficient, but now let's apply our power rule for this. So we've rewritten it. Now our derivative, f prime of x, The derivative of 4, because that's a constant, is going to be 0, so that's going to go away. So we're left with negative 1/2 times negative 2, x raised to the negative 2 minus 1, which would be negative 3 power. So we have a negative 1/2 times negative 2, that's going to equal positive 1. And that negative exponent is going to move down to the denominator. So f prime of x is going to equal 1 over x to the third power. And that's going to be problem number 5. 1 over x to the third power for problem number 5. Number 6, we've got 3 square root of x. We've got a negative 6 divided by x squared. And we've got 5 pi to the third power. Again, similarly, I want to rewrite this first. Actually, I'll be consistent with my colors. So I want to rewrite this first. So g of x, it's the same equation. I haven't taken a derivative yet. This is 3x to the 1/2 power. We know that square roots are functions that are being raised to the 1/2 power. And then this is minus 6x to the negative 2 power plus 5 pi to the third. Again, my goal here is to rewrite this so that there are no fractions and I can apply the power rule as is, right? So we've got sort of no square roots, we've got no expressions in the denominator, so this is ready to use for our power rule. Now I'm taking the derivative, so g prime of x is going to equal 3 times 1/2 x to the negative 1/2 minus 6 times x to negative 6 times negative 2 x to the negative 3, and then the derivative of 5 pi to the third is going to be 0. Even though this has an exponent on it, pi is a constant. So this is whole term, 5 times pi to the third is just a number, it's a constant, and we know the derivative of any constant is 0. So this is sort of a common trick where they're trying to make you think, hey, should I use the power rule here? But this is not a variable, right? Pi is just a number. So let's simplify what we've got. We've got 3 times 1/2 times x to the negative 1/2 power. So that is going to equal 3 divided by 2. 3 times 1/2 is 3 over 2. And then that x to the 1/2 is going to move to the denominator. But we know, again, x to the 1/2 is the same thing as the square root of x. We then have negative 6 times negative 2, which is positive 12. And then that x cubed is going to go down to the denominator to make that exponent positive. So we've got 3 divided by 2 square root of x plus 12 divided by x cubed. That is going to be our solution for problem number 6. Again, these are finding derivative functions, which again mean that if I wanted to find the slope of the tangent line at a specific x value, because I've got this derivative function, all I would need to do is plug in that x value here. Side note, I also get students every year asking me about, are we able to leave radicals in the denominator for a derivative function? It is fine to leave it for the function like this. I would not say we need to like rationalize or multiply by, say, like a conjugate or something like that. We would just not, when we plug in our x value here, we just wouldn't want to leave it as the square root if we're trying to simplify that all the way. So for now, it's fine to leave, but once I plug in a number for x, we would want to make sure that that radical is as simplified as possible. All right, number 7. We've got 4e to the x minus 2 cosine of x. This is already written in a form that I can take the derivative of it. I don't need to rewrite this. So let's jump right into this. H prime of x is going to be equal to, well, 4 times e to the x is its own derivative. So the derivative of e to the x is e to the x. So that term doesn't change. And then we've got a minus 2. And we know that the derivative of cosine is negative sine of x. And so h prime of x here is going to be equal to 4e to the x. I've got a negative 2 times negative sine, so that is a plus 2 sine of x. That is going to be our derivative function for problem number 7. For problem number 8, we've got s of t is equal to t squared times sine of t. So we have this implied multiplication going on, which tells me that we're going to need to use our product rule for this. In these problems, I very commonly find that it's useful to identify my f of x and my g of x. F of x here is going to be t squared, so technically not f of x, but f of t, if we want to be consistent with the variables. So that's f of t is equal to t squared, and we know the derivative of that f prime of t would be 2t. And g of t would be our second function, that's sine of t. And the derivative of that would be cosine of t. We also remember then that the product rule, our product rule, says to do f prime of x times g of x plus f of x times g prime of x. And so we're going to be using that here in that format. So let's take that derivative. Our derivative then is going to be s prime of t, and that's going to be equal to 2t times sine of t plus t squared times cosine of t. And so if we want to clean this up a little bit, there's actually not much we can do. That's going to be just 2t sine t plus t squared cos t. And that is s prime of t. If we were, for example, doing a multiple choice problem and needed to get a particular answer, maybe we could factor out a t out of both of these terms and pull that in front. But really that looks pretty good for this particular problem. All right, let's try number 9. This also looks like a multiplication where I've got 3 squared of t multiplying the natural log of t. So let's do our setup again. Our first function I'm going to call f of t in this case. That's going to be 3 squared of t, which we know is the same thing as 3t to the 1/2 power. And if we take the derivative of that, that means that f prime of t is going to be equal to 3 times 1/2 times t to the -1/2 power if we apply the power rule to that one. If we want to simplify that, that's going to be 3 over 2 square root of t. That's our f prime of t for this one. And then g of t is our second term. That's the natural log of t. And we learned in this chapter that the derivative of the natural log of t is 1 over t. So let's do our, again, product rule setup. Product rule. And again, we're going to do f prime of x times g of x, except in this case t's, plus f of x times g prime of x. That's our setup for this one. So let's plug in what we know. So this is going to be equal to, d prime of t is going to be equal to 3 over 2 square root of t times the natural log of t plus, let's see, f of t is going to be 3 square root of t if I leave that alone, times g prime of t, which that would be times 1 over t. So if we would want to simplify this, that means that d prime of t is going to be equal to 3 ln of t divided by 2 square root of t plus 3 square root of t divided by t. And that is probably as simplified as we're going to be able to get it for this particular problem. So 3 natural log of t divided by 2 root t plus 3 root t divided by t. Great, that's number 9. Number 10. Looks like another one that we've got here where we can rewrite this first term in order to take the derivative for it. So the pre-work, I'm going to rewrite first. Y is going to equal 4x to the -1 power, and we're subtracting that secant x. Now it's set up that we can use the power rule. So our power rule says that the derivative, let me change this up. Let's call this dy dx just for the sake of changing things up. We know we can call the derivative y prime or dy dx, but I want to make sure that we're familiar in writing it a bunch of different ways. So that's going to be equal to, by the power rule, 4 times -1 x to the -2. And then secant squared was, or secant was one of our derivatives that we learned in this chapter. The derivative of secant is going to be secant x tan x. So secant x tan x. So if I wanted to simplify and get my final answer for this one, that looks like that's going to be 4 times -1, which is -4. That x to the -2 is going to move down to the denominator to make that exponent positive. And then we've got a minus secant x tan x. That is our solution for problem number 10. Nice. Number 11. Hey, this looks like a quotient rule problem. I know that it's a quotient rule problem because we're dividing two functions. And this is not, it's not like there's just like a coefficient or just a there's variables in the numerator and the denominator, so I have to do my quotient rule for this problem. So here's a reminder that this is a quotient rule problem. Well, what are my two functions? Well, the numerator is what we call f of x. So f of x is our 2 minus x. If we take the derivative of that numerator, that's going to be negative 1 by the power rule. And g of x, that denominator, is going to be x plus 2. And the derivative of that by the power rule is going to be just 1. So if we apply our quotient rule, if you remember, is the one, I'm going to try to write small, but g of x times f prime of x minus f of x times g prime of x, all divided by g of x quantity squared. So that's our quotient rule. That was from our very last lesson. It was from section 210 in this chapter. Cool, so let's apply it. If we do our derivative, let's call this dh dx, the derivative of h with respect to x. G of x here was what? X plus 2. F prime of x was negative 1. We've got a minus between these two terms. F of x, which was 2 minus x, times g prime of x, which was 1. And that's being divided by the denominator squared. So x plus 2 quantity squared for that. Now, we can do a couple different things to try to simplify. I would make sure first, that we are going to distribute that negative 1 to both of these terms, and then that we distribute this negative to both of these terms. If we do that, we're going to get that this is equal to a negative x minus 2, and then a minus another 2 plus x, and then that's going to be divided by x plus 2 quantity squared. Looks like those x's in the numerator cancel. I got a negative x and an x. So all I'm left with is a negative 4 in that numerator, and that's being divided by x plus 2 quantity squared. That is going to be our derivative of h, aka h prime, or dh dx. Great. Number 12, find the equation of the tangent line of the function at the given x value. All right, so we need to find the equation of the tangent line. In general, when we are writing the equation of a line, whether it's a tangent line or sometimes we refer to as a normal line, which we'll see in number 14, we in AP Calculus use what is called point slope form. So point slope form is the go-to way to write an equation because it doesn't require any manipulation. It just requires knowing the slope and knowing what point that it's going through, which is the most common information that we're going to get in AP Calculus. So a reminder, this is what point slope form looks like, and that we're talking about the point that we know is going to be our x1 comma our y1, and then the slope is going to be our m. And so if we do problem number 12, the way that we're going to want to think about this is, well, first we need to know what point it goes through. We know that it's negative 2x cubed plus 3x at x equals negative 1. So first I want to know what f of negative 1 is. So we're going to plug in negative 1, 2 times negative 1 to the third power, plus 3 times negative 1. Negative 1 to the third is negative 1, so this is going to equal 2 minus 3, which is going to equal negative 1. So our coordinate that we have is going to be the x is negative 1, the y is negative 1. This is the point that we're going to use for this. To find the slope, well, we need to know we're in a calculus class, and we know that this chapter is about derivatives. We learned that the definition of derivative is it is the slope of the tangent line, or aka the instantaneous rate of change. So even though this doesn't directly tell us to do it, we should know that if I want to find the slope, I can take the derivative. And so if we do this, the derivative of f, we're going to call f prime of x, by the power rule should be negative 6x squared plus 3. And I want to find the slope when x is equal to negative 1, so I want to know what f prime of negative 1 is going to be. So that's negative 6 times negative 1 squared plus 3, so that is going to be equal to negative 3. We've got our point, now we've got our slope. So what is our solution here? We're going to use this point slope form that we wrote here. So I've got y minus negative 1 is equal to -3 times x minus -1. As a solution, it's going to be y plus 1 equals -3 times x plus 1. This would be our answer for problem number 12. Again, it is totally acceptable on the AP exam and just generally in this class to use point slope form. I don't need to go any further and like put this into y equals mx plus b unless they ask for it, which they almost never do. Great, number 13. We've got 4 sine of x minus 2 at x is equal to pi. Because I can see that we're going to need to know some trig values at pi, I'm just going to quickly think about my unit circle over here. If we have our unit circle, we know that pi is all the way over here. So if we sort of go all the way around, pi is at this point. That's our angle pi, and we know that that's at the point -1 comma 0, which tells me that the sine of pi is 0 and that the cosine of pi is equal to -1. This side work is going to be useful for us. And again, it is useful to memorize the unit circle and to practice memorizing it because it is fair game for the AP exam and the College Board to ask you questions like this on the no calculator section. They expect you to know what sine of pi is and cosine of pi, and we've got to know our unit circle in order to do that. All right, so similar to the last one, the first thing I want to know is the point that it goes through. So I want to find f of pi. So that is going to be 4 times sine of pi minus 2. As we just said, sine of pi is 0, so that's going to be 4 times 0 minus 2, which is equal to -2. So what coordinate are we dealing with? We're dealing with the point pi comma -2 for the point for this problem. Then we want to find the derivative. So f prime of x, the derivative of this function, would be 4 cosine of x, because cosine is the derivative of sine. And then the -2 is a constant. The derivative of that is 0. So the derivative of this whole function is just going to be 4 cosine of x. What then is f prime of pi? What's the slope when x is equal to pi? That's going to be whatever 4 cosine of pi is, which we can see the cosine of pi is -1, so that's going to equal -4 for our slope for this. Altogether then, to write our equation in point slope form, that's going to be then y minus -2, so y plus 2 is equal to the slope -4 times x minus pi. And that is going to be our final equation for problem number 13. All right, number 14, how's this one different? They have this word normal line. Tangent lines have the exact same slope as the function at a particular point. This word normal, we should remember, means perpendicular. It is a perpendicular line to the tangent line at that particular point. And from Algebra 1 or from just earlier in high school, we should know that perpendicular lines have slopes that are opposite reciprocals. So they are opposite reciprocals. But similarly here, I'm writing the equation of a line. So I'm going to need to use point slope form, which means I need to know the coordinate that it's going through, and I need to know the slope of that perpendicular, aka normal line. So my work for this one, let's first find out what y of -3 is. That looks like that's going to be what? 1/2 times -3 squared plus 3/4 times -3 minus 4. So if we simplify, this is going to be, looks like 9/2 minus 9/4 minus 4. So 9/2 minus 9/4 minus 4. If I'm doing this without a calculator, we want to find a common denominator. So that's going to be what? 18/4 minus 9/4 minus 16/4. So that is going to be -7/4 for that output for this. So that is the coordinate. The coordinate is going to be -3 comma -7/4. And I'll highlight that because that's the point that we're going to need for our equation. And similarly, we need to know what the slope is, which means we need to find the derivative. So what is y prime of x? Well, the derivative of this function, if we have a 1/2 x squared, is going to just be x to the 1. And then the derivative of 3/4 x is going to be just 3/4 by the power rule. And then -4 is a constant. We know the derivative of any constant is 0. So this is our derivative function. Then we need to know here what is the derivative of this function when x is equal to -3. So that's going to be -3 plus 3/4. So that's going to be equal to -2 and 1/4. Or, we can say that that's equal to -9/4. So -2 and 1/4 would be -9/4. So this would be the slope. So I'll mention this would be the slope of the tangent line, which means if we want the normal line, we need to take the opposite reciprocal. So the opposite reciprocal of -9/4 is going to equal +4/9. So we flipped the fraction to make the reciprocal, and then we changed the sign to get that 4/9. So this is our slope of that normal line. And then now we're going to just get into writing the equation using that point slope form. So that is going to be what? Y minus -7/4. So it's a minus negative. That means it's a plus 7/4. And that's equal to the slope of that normal line, which is 4/9, times x minus -3, aka x plus 3. That is going to be our equation for problem number 14. So key piece to know if you're thinking about normal lines is that they are perpendicular, which means the slopes are opposite reciprocals. Number 15. If f of x is equal to 3 times the sine of x minus 2e to the x, find f prime of 0. This is no calculator problem. So they want us to find f prime, so let's take that derivative. Our derivative here is going to be f prime of x is equal to 3 times the derivative of sine, which is cosine of x, minus 2 times the derivative of e to the x, which is itself, it is e to the x. And we want to know what f prime of 0 is. So 3 times cosine of 0 minus 2 times e to the 0. This is, one of these ones where if it's a no calculator section of the AP exam, you're going to need to know, what cosine of 0 is. That's going to be equal to 1. And then our e to the 0, anything to the 0 power is also equal to 1. And so this is going to be then 3 times 1 minus 2 times 1. So that is going to just equal 1 as our answer for problem number 15. A calculator is allowed on the following problems. So if our calculator is allowed on these, we're going to want to use the n derivative feature on these. So our n derivative feature on our calculators, as a reminder, you can find that on a TID3 or TID4 by hitting the math button and then going down to the number 8. So math and 8 will get you to that n derivative feature on your calculator. If we wanted to find the derivative of this f of x function, again, we're going to hit math and then 8. It's for n derivative. And it brings up our derivative sort of like math type here if you're using a TID4. In that, we're going to say we're taking the derivative with respect to x, and the function they gave us was x times sine of, looks like 3x squared, so 3x squared, and then minus 2. So minus 2, we close those parentheses, and then we're going to say the x value that they're asking about here is going to be 7. So we say take the derivative of this function when x is 7. That gives us a derivative of about 260.246. Again, we round to 3 decimal places, or 3 digits after the decimal place in AP Calculus. Using that calculator, again, we can find that f prime of 7 using our calculator is going to be equal to 260.246. Again, if you are using your calculator on that AP exam or any quiz or test in this class, please make sure that you are always rounding to 3 digits after the decimal place. That is the standard in AP Calculus. They will take off points if you round to anything less than 3 digits. So that is really important. Our second one here for number 17, the derivative of cosecant of 3x. We need to remember in this case that cosecant is the reciprocal of sine, so we still hit math and then 8 for n derivative, so it pulls up our derivative math type format here. We're taking the derivative with respect to x, and since there's no cosecant on our TID4 calculator, we need to remember that cosecant is the reciprocal of sine. So I'm going to say 1 divided by sine, and we know that 1 divided by sine is cosecant, of 3x. So that is the input for our sine piece, and that's going to give us our cosecant of 3x. And we want to know when x is equal to 2, so if we take that derivative, we're going to get negative 36.899 rounded to 3 digits after the decimal place. My only reminder for you for this one is that cosecant, right? There's no button for cosecant on your calculator, so we need to remember that cosecant is 1 over sine of x. That's number 17. Number 18, use the table below to estimate the value of d prime of 120. So where's 120? Well, 120 would be right here. You always want to use the x and y values or t and dt values as close to the function as possible. So I'm going to be using those two sets of points. But we're estimating the value, right? I don't know what d of t is. So the best that we can do is estimate it by finding the average rate of change between the 2 points that are closest to it. So what is that going to be? Well, that's going to be 808 minus 412 divided by 180 minus 60. So we found the average rate of change. And that is an estimate of d prime of 120. And if we do that, 808 minus 412 divided by 180 minus 60, that's going to give us about 3.3. And they said indicate units of measure. Key tip for the AP exam, if they ask for units of measure and you don't give it to them, you're going to lose a point. So be careful to look out for those. How do we find the units of measure? Well, the 808 and the 412 were in feet, and then we're dividing by things that were in seconds. So these are feet per second. So 3.3 feet per second for that. And that's going to be number 18. Last two problems for this review. Number 19, is this function differentiable at x equals 2? For these piecewise functions, a general rule is you should always first check to ask yourself, is it continuous? Because if it's not continuous, it cannot be differentiable. How do we check continuity? Well, we think back to chapter 1. Back in chapter 1, we know that the limit from the left and the limit from the right would need to be equal to each other, and they'd need to equal the actual output of the function, in this case when x is equal to 2. So the work that I'm doing here technically is I'm finding the limit as x approaches 2 from the left for f of x, and I want that to equal the limit as x approaches 2 from the right of f of x. And of course I also want that to equal what f of 2 is, if this is going to be continuous. So what does that look like with this piecewise function? Well, that means that this 3x minus 3x squared minus 5 has to equal 7 minus 9x when x is equal to 2, right? Because that's where these two parts of the piecewise function are connecting. And if it's continuous, they should be the same on both the left and the right. Well, let's substitute in and see. So we've got 3 times 2 minus 3 times 2 squared minus 5, and that should be equal to 7 minus 9 times 2. 6 minus 12 minus 5 is equal to 7 minus 18. So that's negative 6 minus 5 is negative 11. And then 7 minus 18 is negative 11. So great, check, yes it is continuous. That's a good first step to check. Now, what would we do if it was not continuous? I'd be done, because we know that if a function is not continuous, it is not differentiable. But now that I know that's continuous, the way that we're going to continue this problem is now we're going to check to see, is this actually differentiable? And again, the reason why we're checking differentiability here is, a function could look like this. Right? A function could look like this. It could have this thing that's called a corner or a cusp on it. and it could be continuous, but it would not be differentiable at that point. So the only way that we could tell that whether it's differentiable or not is we need to compare the derivatives on the left and the derivatives on the right. And so really what I'm checking here is I want to see for the limit as x approaches 2 from the left, is the derivative equal to the derivative from the right side of this? And so that's what I'm technically doing here. This is generally good work to show, to be able to explain why you're doing this. I want the derivative from the left and the limit from the right to be equal to each other. So what's that look like? Well, the derivative of 3x minus 3x squared minus 5 is going to be 3 minus 6x. The derivative of that negative 5 is 0 because it's a constant. And then that's going to equal the derivative of 7 minus 9x, which is just negative 9. We care that these derivatives are equal when x is equal to 2, again, because that's where these two parts of this function are meeting. And so let's plug in and check. 3 minus 6 times positive 2 is equal to negative 9. So that's 3 minus 12 is equal to negative 9. Negative 9 equals negative 9. Great. Excellent. So we know that it's continuous. Now, because these derivatives were equal to each other, we can say yes, it is differentiable. That is our conclusion for this. So again, for these piecewise functions, I would first check to see if it's continuous, and then I would check to see then is it differentiable by looking at the derivatives for this. Last one for number 20, the question is what values of a and b would make the function differentiable at x is equal to 4? Again, similar to this last one for number 19, if it's differentiable, it needs to be continuous, which means that at x equals 4, the two functions need to equal each other. So I'm going to set that up first, the continuity part. And generally in these types of problems, we end up with like two different equations that we're going to have to solve. Let's take a look at it. So a square root of x plus bx squared minus 1 should equal 16 over x plus bx when x is equal to 4. So let's plug in. We've got a square root of 4 plus b times 4 squared minus 1 is equal to 16 over 4 plus b times 4. If we simplify, that means that 2a plus 16b minus 1 is equal to 4 plus 4b. If we wanted to combine like terms, we could subtract that 16b to the other side and subtract that 4 to the other side. So that means that 2a minus 5 is equal to negative 12b. Great. That is our continuity piece. Now this is interesting that we don't know what a is and we don't know what b is, which means we want to jump to the differentiability side and see if that can give us any more information about a and b. So the differentiability side, we want to take the derivatives and we want to set those equal to each other. If we take the derivative of a square root of x, the derivative of that is going to be a divided by 2 square root of x by using that power rule and simplifying, and then plus the derivative of bx squared, so that's 2bx to the 1, and then the derivative of negative 1 is 0. And then we've got the derivative of, this should equal the derivative of 16 divided by x, which is going to be negative 16 over x squared if you do the power rule and simplify, plus the derivative of bx, which is just b. Again, this is going to be when x is equal to 4. That's true for both of these. So we're going to plug in x is equal to 4. So I have a divided by 2 square root of 4 plus 2b times 4. That's equal to negative 16 over 4 squared plus b. So a divided by 2 root 4 is going to be a over 4 plus 8b is equal to negative 16 divided by 16, which is negative 1, plus our b. If I combine my like terms here, this looks like we can say that a to the 4th, actually I'm gonna multiply everything by 4 here. I think that's going to be easiest, well, actually I'll subtract the 8b to the other side first. So a to the fourth is equal to negative 1 minus 7b. And then I'm going to multiply the whole equation on both sides by 4. So a is equal to negative 4 minus 28b. Now, here's what I've got. I've got this equation here, and I've got this equation here. And both of these two equations have to be true. This equation has to be true if it's continuous. This equation has to be true if it's differentiable. But I've got two variables that I don't know what to do with. Since I have these two equations, what we can do is go back and think back to Algebra 1 and Algebra 2. What we technically have here is a system of equations. It's a system of equations that we need to solve. And so bringing back that review from Algebra 1 and Algebra 2, we know that we could solve a system of equations with either substitution or elimination. Either way, your choice. For me, because I've already got this a by itself, I'm going to do substitution. I think it's going to be real easy. I'm going to take this equation, I'm going to substitute it in for the a over here. So this whole negative 4 minus 28b is going to go in for a in that other equation. And if I do that, I get 2 times negative 4 minus 28b minus 5 is equal to negative 12b. So again, that whole negative 4 minus 28b became the a in this equation. By substituting that in, now I have just b's, which is going to allow me to solve for that b value, and then hopefully get to an a value after that. So what do we have? We've got, if we distribute, negative 8 minus 56b minus 5 is equal to negative 12b. If we combine our like terms, that's going to be negative 13. I'm going to add that 56 to the other side. So negative 12 plus 56 should give us 44b, which means that b then is equal to negative 13 over 44. So that is our b value that we would need for this. How do we find the a value? Well, we can then take that and then plug back into our equation here. We know that a is going to equal whatever negative 4 minus 28 times b is. B was negative 13 over 44. So a is equal to negative 4 minus 28 times negative 13 over 44. That's going to end up being positive 91 over 11. And then if we add that negative 4 to it, a is going to be equal to 47 over 11 for this particular problem. So this is exactly what the a and the b would need to be if this original function right here was going to be differentiable. Our a and b would need to be those values if it was going to be continuous and differentiable at that particular point. That's it for our review for today. I hope that Chapter 2 went really well for you. Good luck with your studying and good luck on that Chapter 2 test. Have a great rest of your day.